4 technical universities are on a mission. Students and professors are studying, working, contributing to make the energy transition possible. This is their story.
So what we do here is develop technology for the production of hydrogen, essentially for 2 reasons. One is to store renewable energy when it's available, and on the other hand to produce green hydrogen for the manufacturing of chemicals in the chemical industry. This is the electrolyzer, this is what it's all about. We try to improve the performance of the electrodes that are in there, and also look very closely at the physical phenomena, including what happens near the membrane. Ion transport through the membrane is what we investigate, but also looking at bubbles that grow on the surface of these electrodes. On the one hand on flat electrodes, and on the other on porous media, to see how the bubbles actually improve transport phenomena. With respect to the synthesis of the electrodes, we have advanced technologies like pulsed laser deposition to create model surfaces, but also sputtering followed by dewetting is an important way to create electrodes which are better in terms of performance, stability and cost. And in that way we hope to develop better electrolysis setups for the production of hydrogen.
So here at the University of Twente, we are also working on high temperature ceramic membrane based electrolyzers. These devices, they work at around 500 to 900 C. So obviously we don't have to worry about gas bubbles, but we do have other issues that these high temperatures cause. Thus, here we use advanced physics-based simulations and experimental techniques to investigate phenomena all the way from single cells, as you see here, to industrial megawatt scale systems, and how can they be integrated into industry as well as long-range transportation. By combining these information with AI, we can develop real-time advanced digital twins of these devices that can help us better control and extend their life under operation. So together with the other universities in the 4TU and the work we're doing on low temperature and high temperature electrolysis, I'm convinced that we can make a real impact in the energy transition.
In the future, the extra energy that is produced in the wind farms needs to be stored and used at a later time. Hydrogen makes the storage of energy possible. Hydrogen is a clean fuel, and when it's burned, it only produces water and heat as the byproduct. In a fuel cell, the hydrogen first comes in contact with the electrode, where it's split into 2 electrons and 2 protons. The electrons can be harvested in the form of electricity, and the protons will be permeated through a semi-permeable membrane to recombine with oxygen to produce water. The focus of my research is at the center of a fuel cell, the membrane. The membrane needs to be conductive to protons, so the protons can pass through the membrane while molecular hydrogen is being blocked by the membrane. Currently, the commercial membranes that are being used for this process are mostly based on perfluorinated materials, something very harmful to the environment. So in my research, first of all, I'm trying to make this membrane out of sustainable materials. And secondly, I'm trying to improve or even suppress the performance of the commercial membranes, so these membranes can preserve their conductivity even at high temperatures or low humidities. These conditions are particularly very relevant for the application in industrial settings.
Hydrogen can be used safely, but we need to take some necessary precautions. At the moment, hydrogen detectors exist, however, they don't really do the job. They're relatively big, they're expensive, they require the presence of oxygen, but they also need electric currents typically near the sensing area, which can cause actually a safety hazard. What we do in our lab is that we develop small optical hydrogen sensors that can be made relatively cheap, small, and can detect even the tiniest amount of hydrogen leaking into the atmosphere. We apply a very thin nanometer thickness coating on top of an optical fiber. Part of this hydrogen actually is absorbed by our metal hydride coating. This means that the optical properties change. And for example, now not 50% of the light is reflected, maybe only 40% of the light is reflected. And in this way we can say something about the amount of hydrogen around our fiber sensor. A particular challenge is to quantify how much hydrogen is actually absorbed by our material when they are exposed to hydrogen, which we can for example do with neutron reflectometry. We produce these materials by magneton sputtering, and afterwards we test whether they actually have an optical response when exposed to hydrogen. Recently we developed and patented a material that can detect both very low and very high hydrogen concentrations with just one single material. It can also do that in a very short amount of time, such that we can have a real-time indication of the hydrogen concentration around. It's now our challenge to develop this further into a product, such that we can use it on board of, for example, hydrogen planes.